Mohamed Mankibi, do you give your talk in French or in English?
I will give my speech in French, in English.
In English, okay.
Yeah,
then
but
we will
then
we can continue in English. Okay, so Professor Mohamed Mankibi, he's an expert in building and system performance enhancement, and his title is Building and System Performance Enhancement using Latent Energy Storage. And I want just to give some detail about his biography. He's a research director, professor in France at the ENTPE, is it's École Nationale, that is?
Yes, École Nationale des Travaux Publics de l'État. I will explain it in my presentation. No problem.
Okay. So University de Lyon, that's in France. He's member of the LTDS laboratory. You can also explain this. He has a PhD degree in hybrid ventilation control strategy design and assessment, and accreditation to direct and manage research. So he was the manager of and supervisor of building related course in his school, and co-reactor and co-manager of several and of the master degree related to the green building. And BIM highly evolved in green and low impact building design and optimization program. So it's energy efficiency. He has two major fields of research. One is related to dynamic simulation of thermal and aerolic, or I think, phenomena in building. He will explain to us this in more detail afterward. The other is related to the development of multi-objective optimization. So Professor Mankibi also has spent 1 year as an invited researcher at the University of Colorado at Boulder, as well as at Concordia University of Montreal, and has been involved in many tasks of the International Energy Agency. He has taken part of several national research projects as coordinator or partner, as well as European and international projects. So he has developed several original model and experimental devices and initiated and lead partnership with building industry. So I think if you want to have someone expert in energy efficiency and building, we have it today. And I want to thank him very much that he accepted our invitation, and he will be, I hope, in the future one of our member at the Virtual Learning University. I think he is also from South Morocco, I guess, and we people from South Morocco, we work very hard. So thank you very much, and the floor is yours.
Thank you very much, Professor Ahmed Nawi. Thank you very much also for inviting me to give this, giving me this opportunity to talk about one of the major sectors that is polluting our planet. And my speech is a little bit different from the previous one because he will focus on the how to integrate thermal storage in buildings. So I will focus on a kind of holistic approach we adopted in our laboratory. So the topic is building and system performance enhancement using latent energy storage. I will introduce my university and my lab later in this presentation. But first of all, let me show you the plan of my presentation. First of all, I will introduce the context of our studies, which is related to low impact building. I will give a short description of what is low impact building, and also talk about the potential of latent storage integration in this kind of buildings, and give you some examples of our success stories, what we have developed, what we succeed to set up, and give some outlooks of this technology. So first of all, what we call low and impact buildings, there is a lot of kind of buildings. We are talking about nearly zero energy buildings, positive energy buildings, green buildings, low impact buildings, and so on. But in my idea, there is a common definition for all of these buildings. First of all, they have to be energy efficient, so they have to be to consume less energy and afford indoor air conditions, good indoor air conditions in terms of thermal comforts and indoor air quality. And second point of low impact buildings, they should have minimal ecological and societal and environmental footprints. So there is some aspect to minimize when we are dealing with this kind of buildings, and I think we are facing these buildings in the future because all the countries are expecting to set up and renovate existing buildings to be low impact ones, especially in Europe. So the first impact to minimize is the environmental one. So to reduce what we call the dry energy. And the dry energy is the energy used to manufacture the components like insulation systems and so on. And also to reduce the usage energy. So when we are affording good indoor air climates, we need some usage energy. So we have to reduce it by using efficient systems or integrating, for example, PVs and so on. And also to reduce the impact on the environmental aspect, for example, to avoid impacting the water and the cycle of water, for example, and to avoid what we call heat islands. So a lot of buildings are now producing heat islands because we are using a lot of external units for cooling and heating buildings. So we are even impacting the city. So the problem is larger than systems and buildings. Next aspect to minimize is the societal one. First, to bring good indoor air conditions, as I mentioned, in terms of thermal comforts, winter and summer, indoor air quality, acoustics and lighting, and also to avoid what we call in France la pauvreté énergétique, fuel poverty, because now there is a lot of people who can't afford heating and cooling because it is getting more and more expensive. So this societal impact has also to be reduced. And finally, the economical one. So we have to think globally when you are taking costs. So this is what I call low impact buildings. This is the context of my presentation and to the kind of building I am expecting to apply this kind of latent storage. So continuing with the context, the first question we are asking ourselves is which design for the future? So there is a vision, a common vision. My colleagues already presented this context today and yesterday. And the vision comes from the directives, standards, and labels. So the vision is now net zero energy building. So and how can we do it? The vision gives us some means. First, energy saving during the design of the building and also the behavior, using passive and hybrid techniques like natural ventilation and shading and so on. And finally, renewable energies integrated to the building. So all the directives, for example, EPBD, European energy efficiency of buildings in Europe, for example, and we have thermal regulations in France and so on. All these directives and labels are giving some visions and ways to reach this level of buildings. The next question we are asking ourselves is it feasible and can we dream it? To answer that, yes, we can do it. Why? Because we have technologies, we have PVs, we have storage, we have a lot of things. Professors and other speakers have also demonstrated that we have great potential of development, and we can say that we have the technology, and the technology is being developed. We have the know-how. We know how to model, how to ask these systems, and also we have policies. So we have the vision. We can do it, but the big question is how can we face the challenge? Because we have great discrepancy between reality and our dreams. Why? Because at this moment we are still at the stage of demonstration and research. We have a lot of demonstration, buildings as demonstration, and we have a lot of research, but we are facing a big problem. We can do it at a large scale. So the major international challenge now is we saw that we technically can do it, but there is some difficulties to achieve this large scale. We have some shortcoming about the owners, the users, the tools, and also the operations. So the building is getting more and more efficient, more and more tight, more and more less and less consumption. So even the tools we are developing are not adapted anymore to the new buildings. So we have to face this challenge also. And also we have the standards, policy, and finance that we have to adapt to the new situation. And to ask the last question for the last presenter, why we can do it in Arabic countries? I think one answer is that we don't have a common standard. We don't have a common policy and a common finance, which is done in Europe, for example. European Union has the directives. For example, North American has one, and also Asian countries have their own standards, common standards, policies, and finance and design process. But I think, and I guess in the Arabian countries, we don't have this kind of consortium to establish a common standards adapted to the culture and the climates, for example. There is some to show you that we can do it. We can have green building. We can have low impact building. This is an example of La Tour Oxygène in Lyon. I am working in Lyon. It is more than 100 meters high. It is completely and mostly done with glass and steel, but it is qualified haute qualité environmental, high environmental quality, because it is bringing a good indoor air quality, and also it is low consumption. The next one is in City Tower, the same city. This one have a kind of passive techniques, double skin facade, and it is 200 meters, and it is a kind of demonstration. It is the first haute qualité environmental, high environmental quality in Lyon. And the last one I want to show is the level of district. This is three buildings, which is the first, I guess, the first European district positive energy district in terms of primary energy. And there is three parts. We have residential, markets, and office. And the idea here is to share energy between the three buildings. When the residential building is occupied, we assume that the other buildings are not occupied, so the produced energy from the other buildings is sent to the residential and vice versa. And this one is, I will mention it also in my presentation. We worked on it, and we have a kind of phase change material integration in order to optimize the cooling system. Now we can do it in a large scale. This is an example of Brazilian program, Minha Casa Minha Vida, which means my home, my life. It's a kind of social housing at a large scale. I think more than 350,000 buildings, and you can see that. Yes, I can say that it's ugly in terms of architecturally, but they succeed to do it and to share and to store energy and to use renewable energy at a really large scale. So the goal here is to do it at large scale and to not to be only at the demonstration or research demonstration scale, because the two towers in Lyon and the Hikari project I just mentioned, they are very, very specific projects, but we are continuing in Lyon to build and to renovate building using the classical ways. So now, what is near zero or net zero or positive energy building? It's a building that has a very high energy performance. The required energy should be covered by to a very significant amount by energy from renewable energy. Also, we need a great we have a great need for integrated design to reach that goal. We used to know how to do it before. There is some examples without active systems. You can see here some in Mesa Verde in Colorado, South Spain, here in the north of European climates here, and also here tropical climates and hot climates. So people before they are using natural, they are interacting with the environment, and also they are using natural and ways without active systems. What changed is we uniformized the world. So here, if you say that picture, according to the building, you can tell me which region of the world where those buildings are located. But if I move to what we are doing now, we are using a lot of active systems, so we uniformize the world. So if you can't see which city we are here, for example, because we are using the same means to design and to construct the buildings, and we are not using the interacting with the climates and the culture. So this is what we are facing, and it's a very, very big problem to reduce the energy consumption. The way to solve that is to use what I call integrated design. First of all, we have to put the occupants or the user, depends on the building, at the center, and then we have to think it holistically. First of all, we have to think the envelope that is insulating the indoor air and the outdoor by innovative materials and active envelopes, for example, using passive techniques, as I mentioned. So we have to deal with the climates, and also to use the storage and renewable energy integration in building. And this is the topic of today. And of course, to think it larger than the building, and to think about the green energy for circularity, for example, and also to avoid heat islands and the increasement of cities temperature. And the final goal is to have optimal indoor conditions. I want to stress the term optimal, so because we can't have the ideal indoor air conditions without consuming energy. So we have to call it optimal. So we have sometimes we need to have less comfort, especially in very hot climates or very cold climates, in order to reduce the energy consumption and also in order to really integrate the renewable energies in building. Now, problematics we are facing are like this. So the buildings we are designing and we are constructing are efficient and smart, becoming smart. So we have indoor air management. So we have some antagonists between thermal comforts, indoor air quality, acoustics, especially in summer. It is antagonism between thermal comfort in terms of hot climates and acoustics. So we can't use natural ventilation, for example. We have a problem of occupants' behavior because the building is integrating smart systems, and also we have new and complex systems. So the systems are complex, so we need to simplify their usage. And finally, there is outdoor environments. So definitely, we have to design according to the urban climate. So there is a lot of antagonists, and there is a great need for multi-criteria optimization. So we have to optimize the design. Next problematic, the second problematic is we have new phenomena in buildings. The first one is the emergence of air as a flexible energy vector. We are not using, especially in North European, water as energy vector because the building is tight and efficient. We are using air because the capacity of the air is lower, and also we can use air even for thermal comfort and indoor air quality. And also we have new phenomena coupling like convection, and radiation and storage in building when we are using double skin facades, for example, or biosourced materials with condensation and so on. So what we are noticing is there is a huge lack of models because we are still using the models developed in 80s, 90s, and beginning of 2000. And we need to develop new models. And for the moment, we can model all this phenomena, but it is time consuming. But what we need when we are designing buildings and when we are integrating PVs and renewable energy, we need to compromise between calculation time and accuracy. Because for the moment, even we have very accurate models, but they are very time consuming, or we have very fast models and tools, but they are not very accurate. And now, because the building is getting tight and less energy consumption, we need to reduce and to increase the accuracy of the models. So definitely, we need for a new there is a great need for a new generation of tools and of design tools and models. At the numerical and experimental approach, we have to deal with different modeling scales: the component, the building, and the distance. So it's not the accuracy, but the scale of modeling. We saw a lot of modeling of the components and the materials, but we need also building and distance. And also, we need to assess building and what we have developed using a kind of experimental protocol. We know how to do it in lab, but in situ and real occupational configuration, it's really difficult to assess the performance of what we are developing. So, like the modeling, the assessments, experimentally assessment, performance assessments need to be developed, especially at the level of building, and at the level of occupied building. So it's a very complex system which needs a holistic approach, as I imagine. Now this is a kind of a big introduction of what is happening, what is missing, what has been developed. Now I will show you some of what we have developed using latent storage. Just a quick introduction about the three major techniques of thermal storage we are using. We are using in the world what we call sensible storage. So the storage is done by increasing or the temperature of the medium. The most used medium is water, like hot water tanks and so on. So we can store energy, but increasing the temperature. The next one is the latent storage, which or also the phase change phenomena. So when a material is called phase change material, when it is changing its phase within a certain temperature, between 0, for example, and 100, we call that material phase change material. So what happens is when this material is melting, so when we are heating it, we are storing a huge amount of energy to melt it, and we can retrieve this energy when it is solidified. And there is another kind of thermal storage, which is thermochemical storage. It is based on chemical reaction, but this one is usually used for high temperatures, more than 100 degrees or Kelvin, and I think it's not adapted for the building. Here is a kind of view of the temperature versus energy storage in kilowatt hour per cubic meter of medium. You can see that sensible one here usually we are using water, and we can store less than latent. And here what I am calling phase change material, because every material is phase change one. Commonly we are seeing phase change material, the material who is changing its phase from liquid to solid or vice versa within this gap of temperature, for example, between 0 and 100. And we are also sorption. I forgot to mention it. The phenomena and the chemical one. You can see that sorption and chemical are using very high temperatures, and my idea they are not adapted to be integrated in buildings. So that's why we are using latent or sensible ones. So now I am come to some examples of our success stories. So ENTP, which is École Nationale des Travaux Publics de l'État, is National Engineering School of State, which is member of the University of Lyon. We are a founding member of the University of Lyon, and we are located in the city of Lyon here, the suburban of Lyon, precisely at Grenoble. It's a postdoctorate engineering school and research institute. We have 5 labs, and we are forming civil servants who are going to serve as in the French government establishments, for example. And also we are forming private engineers who are going to do private sector. We have 3 activities: engineering training program, PhD program and research, and continuous education for engineers and researchers, for example. And we are covering 4 fields: civil engineering, green building and sciences, which is my thing, management of transports and territorial link, like, for example, intelligent transportation, ecotoxicity and risk management for environmental topics, and also urban planning and policies. So we adopted, as I mentioned, a holistic approach to say how can we integrate phase change material and latent storage to building. I will show you some example, for example, for how we integrated phase change material to the building envelope. We used a paraffin that is melting at 25 degrees, how we integrated to solve the blackout energy we are facing every winter. We used paraffin with melting at 35 degrees. How we enhance the performance of an absorption chiller with the phase change material, also paraffin which is melting at 7 degrees, and how we used it in the roof and to cool the roofs in summer with the material is melting at 45. And finally, we dealt also with the solar chimneys, how we enhance the performance of the solar chimneys coupled to buildings with 35 degrees also, and air-to-air heat exchanger 20 to 30 degrees as a melting temperature. First one is the usage of phase change material as peak power shifting solution. As you know, in France and in Europe, we are facing every winter a risk of energy blackouts. So the need of exceptional amount of electricity during the peak power periods is becoming an important issue for energy companies because it is expensive and greenhouse gas emitting, and also it is destabilizing the network and risking blackout. The last one we faced, it was in Italy, and it was 5 days energy blackout. The curves are like this. This is an example of a typical consumption of electricity in France in winter. So you can see here by midday, and especially between 6 p.m. and 8 p.m. we have a peak of energy consumption. So what we have developed with the electricity provider of France during this project is a kind of heat exchanger using phase change material that is allowing to shift that peak power. So every winter, the energy providers are scared by this period because the demand is really big. So the significant impact of building sector with heating is responsible for this. So this is why we developed this heat exchanger. The heat exchanger is like this. So it's a parallelepipedic heat exchanger, and we have plates here, several plates. And inside the plates, we put paraffin that is melting at 35 degrees. So the idea here is, and we have between the plates, we have fins, the aluminum fins, in order to enhance the exchange. And the idea here is to store energy, thermal energy, in the phase change material, in the paraffin, during the day, and only use ventilation, not heating, to retrieve this energy during the period of peak power. And in order to assist this heat exchanger, what we have done is we put several sensors in each plate, the beginning, the middle, and at the end of the plates. So the air is coming like this, and we will see how it is melting, and if we can really bring a kind of heating only by ventilation, not using heating, because we are using the stored energy during the day. The material we used is paraffin, called the Microtech 37, because it is melting at 37 degrees, and the heat fusion is more than 200 kilojoules per kilogram, which is bigger, much bigger than water. This is what we have designed. We have the heat exchanger with the phase change material, and we have fans and heatings. And this is the duct who is going to the building to heat or to ventilate the building. So during the day, we are using the heating and the fans to store energy and to heat the buildings. And during the critical period between 6 p.m. and 8 p.m., we are setting off the heating, and we are only using the fans to retrieve this energy. So in order to assess it, we put temperature, relative humidity, and airflow meters, and also we coupled it with a test cell, a real dimension test cell, which is a big a big room or a big living room. So we have also a bypass. This bypass is used in summer, for example, when we are not using this heat exchanger. And we developed a model using MATLAB Simulink in order to parameter. This is what is happening with the heat exchanger. So this figure is the behavior of the material, the fission material. You have here the time in the x axis and the temperature in the y-axis. And here, for example, when we are heating the fission material, you can see that the first point here is increasing, and here at this moment we have the phase change, so the temperature is getting stable. So we are storing energy here, and we are storing another energy at the middle, and another one here, and then we can, when we have the stable curves here, we can see that we stored maximum of energy. And then when we are cooling, we are retrieving the energy here. So we have the temperature is dropping until 35, and then the temperature is stable. So we have up to 2 hours where the temperature is stable, and of course we have some supercooling, which is characterizing phase change material. So the idea here is to maximize this period when we are retrieving energy. We coupled it with this test cell or this room. It's a little bit complicated figure, but I can explain it. We have the time in x-axis and temperature in y-axis. And here in blue, the indoor air temperature. And here we have 4 days, day 1, day 2, day 3, day 4. And in green, we have the critical period between 6 p.m. and 20 p.m. So here we have the inlet temperature, and in red, you can see we have the heating. So we are heating outside of the critical zone, and between 6 and 8 p.m. you can see that we have no heating, but the temperature is not dropping, because we are retrieving in the energy stored, and we can see it here also and here. And in order to compare with and without the heat exchanger, you can see that when we don't have the heat exchanger and we are stopping heating, there is a temperature is dropping very, very fast. So we cannot only use ventilation without heat exchanger. So we proved that during critical periods we can stop heating and using only ventilation and retrieving energy stored. And in collaboration with the energy provider is making that energy is cheaper in this period and expensive in this period. So he is pushing us to use ventilation. So we can say that definitely we proved, and now it is commercialized with the energy provider. We can use it in order to avoid blackouts. So the big problem with the phase change material is the melting zone depends on the airflow change. So when the airflow is big, the melting zone is not the same. Here, for example, we have the temperature in x-axis and the capacity of the material in y-axis, and we can see here in red when we have a rate heating of the 0.15 degrees per minute. So we have very low airflow. The melting zone is at 35, and if we are increasing the airflow, the melting zone is wider. And if we are increasing to 1 degree Celsius per minute melting, the range is even wider. And this is the cooling system. So there is also the same phenomena when we are cooling the phase change material. So the big challenge now is to find an optimized melting zone to stabilize this difference between depending on the airflow change. So we used. I will pass really quickly by the MATLAB model we developed. So we developed a kind of very complex model in order to characterize the phase change of these plates. I will go really faster because I think we don't have enough time. We are taking into account the air and containers, aluminum containers, conduction. We have also the conduction in the phase change materials and temperature rate change in the medium. So this is the most important is to show you how accurate are our models, because we need them to design the systems. Here we have 3 curves and experimental in continuous simulation in continuous curves, and dot curves are experimental. You can see 3 different here airflow. Here you have time in X, Y, and X axis, and temperature in Y axis, and you can see that we can have approximately a very nice the simulation fits very nicely the experimental results from the tests. So you can see that we resolved that problem of peak power between 6 and 10, and also we have the numerical and experimental test band to use that. The second one is what I mentioned, the Hikari system. Hikari is in suburban of Lyon, and it's 3 buildings. This is another project, and we used phase change material in order to enhance the performance of an absorption chiller. You know, absorption chiller, we need a kind of thermodynamic source, which with that very stable temperature to increase the performance of heat pumps and chillers, for example. So this is what it looks like, office buildings, commercial buildings, and residential buildings, and we are using this absorption chiller to cool them. And in order to optimize the performance of the absorption chiller, we use phase change material. This is the dwellings and office and shops surfaces. We have almost 12,000, more than 12,000 square meters of surfaces, occupied surfaces. And this is the multi-energy system of this building. We have it's really, as I mentioned, it's the first positive energy district in Europe in terms of primary energy. We have renewable energy, we have solar, we have biomass, we have groundwater, and also we have photovoltaics, which with the electricity, we have cogeneration by biomass, called the oil. We are producing electricity, and the produced heat is injected for domestic hot water and heating, and for absorption chiller, we are using the coal. So what I will present today is how to optimize this absorption chiller using phase change materials. This is an example of electricity and storage, and sensible storage with water, and the cold storage with phase change materials here. What we have used is a kind of gel stick, which is melting at 7 degrees, and we put them in a kind of bucket, and then we use several buckets like this. And the idea here is to come with water, because we are using water for absorption chiller, and the water is melting the phase change material here, and here we are retrieving the cold water. So the idea here is to use a huge medium of phase change material. You can see the image here, and to make it approximately stable at 7 degrees. This is an electrical scheme of what we have done. And in order to study that, we produced a kind of small prototype or scale model experimentally. So we used a Cryostat, and we used one bucket with several sensors to add the same idea as the previous heat exchanger in order to model it and to characterize the behavior. You can see what we have done at the level of laboratory. We have the bucket with gel sticks of fission materials, and we come with water here, and we put a lot of sensors at this level, that one and that one, and we characterize the behavior of the fission material, and also we produced a model. So show you the model we developed. So here in red, in XY we have time, x-axis we have time, y-axis we have temperature, and here the behavior of the real behavior, experimental behavior in red of the phase change material. In blue we have our model, and in green we have classical model, namely in the energy plus model, and you can see that with sensible phase here, the classical model is fitting as well the experimental, but it isn't able to fit with the experimental. We are changing the phase, but our model is describing very well the behavior of that. So we use this model in order to design the whole system of Hikari. So we have here, for example, for two buckets, we have the prototype experimental and our model, and how it fits the behavior. And then I used genetic algorithms in order to optimize the melting temperature, number of buckets, number of gel stick in every buckets, and finally it is optimized. We have this result, for example, for the energy need of the building for 1 week. So before introducing fission material, it was almost 80 gigawatt hour, and after we decreased it to 30 gigawatt hour. So it is huge energy reduction, and also the sum of difference between the chiller, cold and hot inlet water, because we decrease it with almost 1 degree. So, and as you know, this difference between the inlet and outlet of the chiller, if you decrease by 1 or 2 degrees, you can reach this kind of energy reduction. And here you have the final Pareto scheme of genetic algorithms that we used. So we reduced by 7% the difference between the inlet and outlet of the chiller, and also by almost 60% the energy needs for the building for 1 week. And another example, and I will be quick here, is the usage of phase change material that we performed at the level of the envelope. So envelope, they have to be tight and resistant, and also you have to have some inertia, especially in hot climates. So concrete is a very nice material with the heat storage, sensitive heat storage, but I think it's not enough. So that we developed a new concrete, textile-based concrete with phase change material. So it is not reinforced using steel, but reinforced using textile. It's specifically for innovation. And then we have green mortar and a textile, and we mixed also this mortar with a kind of phase change material in order to increase the inertia of the envelope. And we have done multi-scale experimentation and characterization with characterizing phase change material using a DSC tool. We used the hot guarded box in order to characterize the thermal resistance and inertia of what we have developed. And also we tested this system in twin cells in our laboratory. We have a cell A, which is a big room, compared to a cell B, which is the reference with the conventional concrete. Here is the curve of temperature melting of phase change material we used. So you can see that it is melting at 25. Here the energy stored, and also it is solidifying at 20 and 50. So it is interesting because it is not melting and solidifying at the same temperature. So we can use it to store higher temperature in summer, and when we are cooling it, we are cooling the building either. So we also increased using that concrete the thermal resistance of building by 25%. So we have, for example, the classical concrete, and when we are using 10% of HTM material, 15% of HTM material, and 20% of HTM material, and you can see the decrease of, in blue here, of conductivity. So we are increasing the thermal resistance of that concrete. The thermal conductivity here, we decreased it for 1.2 to almost 0.7, which is very close to a kind of insulating concrete. So we really divided by 2 the losses in the envelope. And here you can see what we have done in the test cell. We put a lot of sensors, surface sensors, on the outside and inside face of the wall, including, and we have temperature and comfort measurements with the radiant temperature, humidity, CO2, and velocity, and you can see the difference. We have 1.5 difference peak between the cell A and cell B, and also we have a kind of delay of almost 2 hours between the peak of the heat with this configuration. I think this configuration is 10% of this material, but what we are facing now is to optimize also the mechanical resistance, because when we are using HTM material in concrete, we are also reducing the mechanical resistance. So I think the last one is phase change material as passive technique to enhance active solar chimney. This is a collaboration with Spain and Mexico. So the idea of the solar chimney is to use the greenhouse effect in order to cool the building. So when we have a chimney like this here at the middle, we put a glazing, and then we are creating a greenhouse effect at the level of the envelope. So the density is lower, so the heated air is going out, so, and it is creating a kind of airflow through the building. So what is happening is, it is very nice when you have summer sun, but if you don't have sun, there is no greenhouse effect. So the idea here is to put fish tint material at this level, at the level of the wall, in order to heat them and store sun energy and continue to use this effect, buoyancy effect, even after sunset. This is what we have done. So you have here, for example, the time in X axis and mass flow rate. So the ventilation induced by solar chimney in Y axis, and you can see here in black curve is the classical solar chimney. You can see here, when you have sun, the airflow is almost 30 meter cubic per hour, which is nice for a room, for example. But as soon as the sun is went, so the sunset, there is low airflow because there is no greenhouse. So what happens with phase change material is we can increase up to 60% airflow with phase change material. So we are increasing the temperature even when we have sun, but when there is no sun, the phase change material remains warm or hot, so that we have a kind of mass airflow mass even in the night, which will cool the building. So we increased also the behavior of solar chimneys, which could be very adapted for the south of Morocco, south the Mediterranean or even the Arabian countries, which is adapted for these Arabian countries. And the last one is what we have done with China, with the Yunnan University, the vertical air-to-air heat exchanger. So we enhanced also this heat exchanger by using phase change materials at 25 degrees. So we put it in, it's a kind of coaxial ducts, and between them we put phase change material which is melting at 22 degrees. So it keeps also the air temperature at a stable temperature when we are introducing it to the building. So I tried to make it very, very fast with what we have reached with this integration of phase change material. So as a conclusion, there is a great need of further research. Even if we have done a lot of things, it is feasible. We demonstrated. We need standards for phase change material characterization. We don't have any tools in the standard to be integrated in building. It is flammable because it is paraffin. It's like candles, and we have to study the confinement and to avoid combustibility of this material. We have to avoid also leakage to avoid some problem of indoor air quality. This is the problematics and further research topics, and also the paybacks, because 1 kilogram of phase change material is about $20 at the moment. And also the idea is to continue developing integrated design and operation tools. So outlooks. Now we are going toward a kind of holistic approach with data mining and cloud-based management. This is what we have done in a European project called HEART for renovation. The idea here is to use phase change material for storage, insulation, and phase change material in the envelopes. All the techniques we have developed, and also tiles, PV tiles, which are directly connected connected to heat pumps. These heat pumps, it's a kind of self-consumption, and the whole system is managed by what we call a code-based platform in order to integrate the occupants' behavior and manager behavior. And we tested that in 2 locations with 25 buildings in Italy and 25 buildings in Lyon with the social housing company. This is the methodology we developed. So this cloud-based platform has been developed at the beginning before renovating the building. So there is a communication with the construction and stakeholders, the funding stakeholders, and the management stakeholders before the design, and after the design there is a communication with the data and forecast, and also the grid in order to send the extra energy to the grid, and of course user interfaces, either by using smartphones or a simple display at the whole of the entrance. And the idea here and the success of the project lays on the information and mutual action between the occupants, systems, and also the manager. We are still monitoring and analyzing the data of this system, and so I think we will finish with by end of 2020. And what is the future? I think also the future is to use this phase change material say that let's return back to the nature and mimic it using biomimicry systems, especially in envelopes and systems, in order to mimic how natural systems are evaluated, how they are evaluated, brainstorming. This is the idea, for example, of the cloud-based management, and also to discover some models and to apply them to the system. For instance, we are using this in architecture. There is a lot of building architecture that are mimicked from nature. This is what we call biomimicry. But the idea here is to go further and apply it to the system. We have done that with the University of Colorado because we mimicked the body using fashion material and nanogels as a holding material, and we mimicked the skin of the building and the heart. You know, the human body is keeping the temperature at 37 degrees using the heart as a pump, and also blood and skin and a lot of mechanisms. And we mimic that, and we developed a kind of toolbox under MATLAB Simulink, and we demonstrated it at the level of one experimental cell, and we succeed. It was financed by NFS, the National Science, NSF, the National Science Foundation of the United States, and La Région Rhône-Alpes in France. And we succeed to have a system that is mimicking the body skin with blood recirculation and storage, and we are affording good indoor air quality and thermal, but it is still very, very expensive. Probably we can use it for space shuttle or other things, but for the moment, for building it is very expensive. So I would like to thank the people who are behind the scene. Didn't perform all that projects without my student. There is some people who worked with me. They are real heroes of the researchers, and I am just managing the researcher. I would like to thank Miriam, Nadia, Leticia, Leo, Carlos, and Gabriel, and lot of other students who are not displayed here. And thank you very much for your attention. Thanks.
Thank you, Si Mohamed, for this very rich talk on building the green building, or the green in the future. I think we know if we need an expert on green building and passive building, and we know where we find it. We find it in Lyon. So now I will give the floor to Salem, to Ustad Salem, and let's
Thank you.
Go forward.
Thanks, Prof. Mohamed, for your presentation.
Go ahead.
Now here, nothing related to the Q&A. It is open for the questions. Back to you, Prof. Ahmed.
Yeah, I wonder, because phase change material, I heard a lot about it, and do you think it can be the material for the future, the phase change? And if yes, which one? I remember when I was a student, we used paraffin.
Yes.
To do some work. When I come to Morocco, I tried to make some experiment with paraffin, but I don't know exactly if it's really a good material. And also, what about the homogeneity of the temperature when you, because it's not a question of 1 square meter or something, it's a question of a lot. So how you manage this, and which phase material is the most cheaper, and so on?
No, you're right. There is a lot of research gap still, and a lot of locks to remove. we can also use fatty acid, for example, as phase change materials. Not only paraffin, fatty acids are more stable than paraffin.
What is the name? What's again?
Fatty acid is acid gras.
Ah, okay, fatty acid. Yeah.
So we can use that, but I don't think that we can qualify those materials as the material of the future, because we started to study this materials since ETs, you know, and I think what we have to say is how can we use that materials in order to integrate them in the design procedure, and how can we use them in order to solve some intrinsic problem to the related to the weather. So we succeed to do that in a large scale. So the district scale, we used almost 350 kilograms of phase change material. So there is still some problems, like for paraffins, there is 5 problems. There is some indoor air quality, but if you use fatty acids, they are cheaper, for example, but there is some problems of corrosion of containers. If you put them in a containers, there is a corrosion. I think there is 2 ways of research for this kind of materials. The chemical research, how to make them stable, as you mentioned, because it's like if you use a phase change material, for example, that is melting at 25 degrees. If you have 100 cycles or 200 cycles melting solidification, this melting temperature is moving, because the phase change material is not pure. So, but if you are using a pure phase change material, it's more expensive. So the chemical research should be done at this level, and in parallel, for example, designers have to solve the containers problems to avoid the leakage, for example, to avoid the corrosion, and also to reduce the amount of phase change material. I think I can qualify them that as a kind of material that we can rely on in order to reduce or to solve some weather problems. For example, sometimes you have solar when you don't need it, so you have to stop it somewhere. Sometimes you have you don't have a lot of PVs, so or a lot of solar. We have also used these phase change materials to reduce the PV temperatures. There is some what we call them hybrid panels with PVs and thermal systems. So I think if you make a kind of literature review, you can see that we started to study these materials in 80s and 90s, and we stopped to study them because we found other systems, and now there is a new interest in integrating this. There is even 3 international energy agency annexes or projects dedicated to that problem. And in my idea, it's a part of solution. It's not the solution of the problem. It's a part of solution, because I mentioned it. We have to think the solution holistically: occupants, building, districts, even cars and transportation and storage. Okay. It's holistic.
Thank you very much.
If there is any question or comments from the participant, you can raise your hand, or you can write in the chat. I think we reached to the end, Prof. Ahmed. You can go.
Okay. So thank you very much, Si Mohamed. I hope we will keep in touch for other possibility, other course.
Thanks a lot for inviting me and giving me this floor.
Welcome.
And I would like a lot to thank the people who are behind the scene, PhD students and master degrees who are doing a very, very nice work. Thanks a lot for that.
Yeah, sure. Okay, thank you very much. And maybe Dr. Ustad Salim, you can conclude this the whole thing and say some word. And then
just so we say thank you for all the speakers and the participants and the guests in the 3 days of the VLU conference. It was really enjoyable days and with the lectures that we had it. So we hope, inshallah, we see you soon in the coming programs and events, inshallah. So the conclusion to you, Prof. Ahmed.
Okay. So I would like to thank again my colleague in Casablanca who take care of our exhibition in the Expo, that especially Jamila and Nafila, they have been there. They print the old posters and they make a lot of advertising for our university, and also the speakers who went to Casablanca and they gave their talk, and also the manager of the exhibition who gave us this opportunity to be there. And thank you for everyone who attend our Zoom meetings, and I hope to see you soon. Thank you very much.
Thank you. Ma salama.
Okay. Thank you very much.